We're now ready to put the LDA into action. Let me remind you where we left off. We started off with two classes, the blue classes and the red classes in this two-dimensional space characterized by two features, F1 and F2. And we said what we're looking for is to project the data onto a space such that we maximize the difference between the two classes. Why? We're trying to do classification. We want to distinguish them and minimize how much those classes spread to keep them bundled up together. We framed that, let me remind you the notation, xi and yi are the underlying data points here in a two-dimensional space. We have nx and ny of them respectively. And we built these two matrices, SB and SW, which were the between class variance, how much things are spread apart, and the within class variance, which is how bundled they are together. And then what we said, without proof by the way, is that the generalized eigenvector E with the maximal eigenvalue lambda is the vector that when you project the data onto that will, in fact, maximize the spread across classes and keep the classes clustered together. So let's see what that means by that. So first of all, what is the eigenvector? These matrices are 2 by 2 because we're computing covariance matrices. And covariance matrices for two-dimensional spaces are two-dimensional. So this is just a little 2 vector. And so that means you can just think about it as some vector in this space. And that vector will correspond to a line so that when we project the data onto that line, it will keep the data tightly clustered together and keep the classes far apart in an optimal way for this linear projection. So note here, for example, in this case, the data were spread out like this. This is exactly what the intuition was, but again, I didn't fit a line to the data. I fit a line that maximized the objective of maximal classification. That's a very different type of objective. So how do we project the data onto an eigenvector? Well, that's easy. Take every point x sub I in the two-dimensional space, take a dot product with the eigenvector, and that's going to give me some scalar value, let me call that x hat, which corresponds to these values on a one-dimensional now subspace of the full space. And by the way, if I was in a 10-dimensional space to begin with, E would be a 10-dimensional vector, but when I project onto that, I get a single scalar value. So regardless of what the dimensionality is, when you have two classes, you're going to project onto this single vector, and you essentially have reduced this to a one-dimensional problem. Same thing with the y class. Project the data onto the generalized eigenvector, and we get a scalar value, which corresponds to those red points here. And now let's just do classification. Now we've done the hard work. Well, how does classification work? Is we just want to draw a division somewhere down the middle. Now, where should I put that threshold? So what I'm going to do is, so notice, by the way, that with LDA, unlike the logistic regression where it was bounding between 0 and 1, there are no guarantees here. So now we have to impose that binary classification. And the way we're going to do that is with some threshold that says everything to the left is one class, everything to the right is another class. Now, where should I set that threshold? Now, here it's easy because the classes are really well separated. But more often than not, the data is going to look like this. There's going to be some messiness. Some of the red points are going to be over too far to the one side, and some of the blue points are going to be too far to the other side. And you have to decide where you want that threshold to be to build a class. So let's talk about that a little bit. So what I've shown you here, these two distributions, just to give you a sense of what the distribution is of the projected points on this axis, because we can't see that they're tightly clustered. And if things go well, you'll have a big mass on one side for one class and a big mass on the other, but there will invariably be a little bit of overlap. And so we could just pick a hard threshold and hope for the best, or we can think about what happens as we slide that threshold through here. And that's the more standard way to quantify the efficacy of your classifier using so-called receiver operating curves, or ROCs, which is what we're going to talk about right now. So imagine going all the way to one side and picking a threshold and saying everything to this side is class 1 and everything to this side is class 2, red, blue. And then asking, okay, for that threshold, how well did I do? What is the false positive rate and the true positive rate. Remember what a true positive rate is, I'm going to call the red class positive now, is that I correctly classify a red point as red, and a false positive is I incorrectly classify a blue as red. So let's go up to that threshold there and see what happens. What's the true positive rate? Well, I didn't classify very many of the red points as red because I've said only these points are correctly classified. So my true positive rate is really low, somewhere less than 20%. But my false positive rate is also really low. Why? Because there are no blue points over here. I've been very, very conservative. So some good news, bad news. Low false positive, but low true positive too. I missed an awful lot of things. All right, what if I slide that threshold over a little bit? Oops, let me go back one. So now my true positive rate has gone up quite a bit. Now I'm getting close to 60% because everything now to this side is red. And I've increased the false positive, let's see, maybe just ever so slightly. Maybe there's one data point here, but I'm still not in a lot of trouble here. So that's good news. And of course, as I move a little bit more, my true positive rate keeps going up because more and more red is on this side. But now I'm starting to increase my false positive rate because some of the blue is slipping in on the other side of that threshold. And now I've got almost a perfect true positive. Everything that is red is classified correctly, but now I'm starting to eat into that blue distribution, so my false positive rate is going up, and then so on and so forth. So this is the so-called receiver operating curve. And what's nice about this is you could certainly pick a threshold and say, here's the accuracy of my classifier, but it doesn't really characterize the full classification. And so these ROCs you will see are very standard. They have the false positive rate on one, true positive rate on the other. Obviously, you have to tell me which is your positive class and your negative class. And then this thing can be characterized by a single number called the area under the curve, the AUC. So the area under the curve is exactly what it sounds like. You integrate all of the mass under this yellow curve. And if you have so obviously if this curve, by the way, what is the best possible scenario? The best possible scenario is you start down here with a 0 false positive and you immediately shoot up to 100% true positive and then you stay there as you go along. So if you had something a curve that was essentially a corner here, your area under the curve would be 1. Why? Because this has an axis of 0 to 1, normalized from the percentage, 0 to 1. And then I have a square, and the area is 1 times 1. If you have an area under the curve between 0.9 and 1, that's considered a very, very good, almost an excellent classifier. If the area under the curve is 1/2, let's see what's happening here. Well, why is this 1/2? Because I've cut a unit square in half, and so the area under the curve is 1/2. Basically, you have failed here. Why? Because you're guessing. For every true positive, you have a false positive. If I have a true positive rate of 80%, I have a false positive rate of 80%. I'm just guessing at this point. So 0.5 and slightly above is considered a failure, and 0.7 to 0.8 is considered okay, fine, but not great. And so this is just a back of the envelope calculation for how you can think about what your classifier is based on this AUC. It is by no means a perfect way. We saw the F1 score, which is popular also. There are many different ways of characterizing the accuracy, and a lot of that depends on your literature. Certain literatures think more about AUCs, other ones think more about F1, others prefer to see the precision and the recall that we talked about earlier. All right. So now we've done least squares regression for classification, we've done logistic regression for classification, and we've done linear discriminant analysis for classification. There's something that, despite the fact that they're doing very different things in terms of their optimizations, there's something in common in all of them, which is that they are linear. The least squares was a linear model. The logistic regression was a linear model with a sigmoidal nonlinearity. LDA, linear discriminant analysis, was linear. Why? Because we projected onto a line, and so that is going to, at the end of the day, what is nice about those techniques is that they're clean, they're analytic, and you can solve them very, very efficiently, but they are going to have limits in terms of how much they can capture complex interactions in your data. And what we need to start now thinking about is how can we extend into more complex classifiers, and that's what we'll start thinking about when we come back.